So in the previous class, we started this single stage contactor. All right. So the idea was essentially to show that entire this extraction consists of two parts, two units. One is the mixing, where you allow the feed and the solvent to come in contact, and then you have a settler. All right, where you separate extract from this raffinate. So we made a material balance for the mixer as well as for this extracted units, all right, or the settler units. And then we marked the raffinate point, extract point, and we show that we can apply the mixing rule as well as the line falling on the tie lines, or the coordinates on the tie lines. All right. So we'll just go over this very shortly once again before we start switch to this multi-stage contactors. So what we had earlier was, in the previous lecture, single stage contactor. So we have M1, all right, and here we bring feed XF in contact with solvent, let's call it B, or you can call it S sometimes with YS, and then they are in contact, then we separate, and we have this raffinate phase with the coordinates as R1 and X1, and then we have this extract with E1 and Y1, and we say that if it's an ideal contactor, then they are in equilibrium. All right. So essentially here we said that we must realize that this consists of two different units. So in the industrial, you will see there is a mixer where we bring this feed in contact with the solvent, and so this contains both F or B. B may be pure, but B may contain some amount of C. F contains some C. We allow them to mix it. Then there is a settler here. So when it settles, then there are two phases. One is extract, one is a raffinate, and there is a transfer of C solute from one phase to another phase. And then we marked on the different coordinates on this equilateral triangle. So we have A, B, and we have C here. Thermodynamics tells us there is a phase diagram. We start with F, so which is XF here. This is mixed with certain amount of solvent. Maybe solvent is not pure, and this has contained some amount of solute C here. So when we mix this feed with the solvent, say B here, or S1 we can call it, for first stage S and then 1, then we can apply the mixing rule to find out the exact location of this XM, okay, the concentration of solute in this mixture. And then so that's about the first stage. Then you have settle, and then you have this equilibrium. So then look for the tie line which passes through this M. So the same amount is now getting distributed. So one time this material balance is applied along this line connecting between F and B, you can apply the tie rule to determine the location of this XM, and then you have another line which is the equilibrium line, tie line, going through this M. So you have extract, which is E1 here, and you have this R1 here. All right. So essentially, when you write down this material balance, you can say that you have F plus S1. So S1 is the amount of the solvent which we are using as B here. This equals M1, and this will also equal E1 plus R1. So this is one unit, and this is the second unit. Similarly, we can write down the species balance or the solute balance. We have FXF plus S1, YS, then you have M1, then you have XM. Then you have separation between extract, and we have this raffinate. So again, you have this mixer here, and then you have this settler here. And then we can apply this tie rule along both operating lines as well as this equilibrium line. So this would be the operating line. Here you're just mixing it, and then you are separating it, so you have this equilibrium line here. So we can write that S1 by F, the amount of solvent added to this feed, will be equal to XF minus XM1 over xm1 minus ys. So essentially, if we go back to the diagram, we have connected this xf to this ys, and we have located this xm1. 1 means first stage. Okay. So essentially, the most general case would be that feed is given to us. We are adding certain amount of solvent. Feed has certain composition xf, and solvent has certain composition of solute here ys. So from here we can get xm. Mathematically, we get xm here, or from this segment, this ratio to this ratios will be given by s1f. We can also locate xm1. So we can do geometrically, or we can solve for xm1. Once we have xm1, then we are looking for a tie line which passes through this to give you this E1 and R1. So we can write similarly E1 over R1 as x1 minus xm1 over xm1 minus y1. So idea here is that this is your y1 and this is x1. So once we find a tie line which passes through this xm1 is already known from here, then y1 and x1, they are fixed. So this is known to us. This is known to us. xm1 is also known to us. They are with the equilibrium. So we can find out what is the ratios of extract and raffinate formed here and here. So the problem can be rephrased different ways. The idea here is that you must not forget that whatever balance we are making it for total balance or the species balance, we are doing it twice. One for the mixer and one for the settler. One for the mixer and one for the settler. On top of this, we are saying that x1 and y1, they are in equilibrium. So this is the extra constant we apply for this ideal state. So essentially we have one equation, we have second equation here, third, fourth, and we can also say that we have the fifth equation extra constant for the equilibrium if it's the ideal state. Alright, we will talk about the efficiencies and inefficiencies in the later class. Now we will address here the minimum amount of solvent required. Okay, so you should recall and try to compare what we had in case of absorptions when we said that what is the minimum amount of solvent required to absorb certain amount of gas from a gaseous phase, certain amount of solute, say sulfur dioxide from gaseous species. So similarly here we would like to address what is the minimum amount of solvent required for an extractions. Alright, so here we will address again geometrically. Try to understand this before we put down some equations here. So we have A, we have B, we have C, we have again this phase diagram. Alright, and let's take a general case where we have this feed, and let's say solvent is not pure, we have this YS. So this is YS, or we can say S1. Alright, and here we have F and we have this XF. Then we have this mixing. So this tie line passes through this. We have now extract E and we have this R, or E1 and R1. Now let us monitor the locus of this point. What happens if we increase the amount of the solvent? Alright, so if we increase the amount of solvent, you will expect that this line, this xm, will move towards this apex B. Mathematically also you can write down the expression for S1 into F. For a given amount of F, if I increase S, then let us locate the locus of xm. Alright, this will give you the same result, that by increasing this amount of solvent, this line will pass through this. So then again you will take another tie line which passes through this to give you another extract, another raffinate. Let's take this second case where now we decrease the amount of solvent. So now we want to decrease the amount of solvent. Now when it decrease the amount of solvent, now this line will pass through this. So now we have another tie line. So essentially we have this locus of this mixing point moves in this directions. So the question is, we are asking here to what extent we can decrease this amount of solvent. So follow this locus. Now this xm1, maybe 2, maybe 3 here, and then there will be a limit. Say we increase here, then we have reached almost this intersections. Let's call it D here. So you can make out that the last or the minimum amount of solvent will be decided by the tie line which passes through this D point. So the intersection of this feed line, which we can draw like this, and wherever it intersects with this equilibrium curve. From that you take a tie line and pass through this. This will give you the minimum amount of solvent required, because that's your phase. This is the heterogeneous region. This is a heterogeneous region. Here you have this homogeneous regions. So at the most you can go to the extent of reaching this D, which is the intersection of the line connecting with the feed and this solvent here. Alright, so once you fix the mole fraction or the quality of the solvent, this coordinate is fixed. Once you have fixed the quality of the feed, this point is fixed, you can connect with the line, with this straight line. Now given the amount of F, if you keep on increasing the amount of solvent, the XM has to fall on this straight line. So your mixing point moves in this directions till it reaches D. From here you find a tie line which intersects this equilibrium curve at G. Okay, so that means we can write now S1 over F. This is nothing but, in general, the segment FM. So let's take a general FM here. So of how much is the amount of solvent is nothing but this ratios of FM divided by the other segment, which is M and S1. Right, so this segment this by this, that's the amount of S1F. So what is the S1F minimum? All right, so what is S1 over F minimum? Wherever we have this intersection of tie line going through D and G, so we have FD over DS1. So that's the segment. All right, so maybe you can draw this phase diagram, and we are saying that this is the line, originates from F, ends with solvent S1, and we have reached this location, that's the limit where we have this G and we have this D here. Okay, so this will give you the minimum amount of solvent. So that's the ratios FD over this DS1. This ratios divided by this. That's the amount of S1F over minimum. And this will also be equal to, by mixing rule, XF. So we have this XF here minus XD, that's XD, you can read from the graph, divided by XT, minus you have this YS1, the coordinate of this point. So this will give you minimum amount of solvent required. Now we should also make a note here that at this limit, where you have the tie line passing through this D and G, you have very small amount of extract. So this all coordinates which you had here in several tie lines, this was your extract, and this side you had raffinate. Okay, so here we have reached an amount. Now this when the tie line passes through this mix, again we can find the ratios of extract over raffinate as the ratios of this over this. So in this limit where there is no segment left here, all it means that we have very small amount of extract at this point. Of course, this is a very hypothetical case. Whenever you want to apply a tie rule or lever rule, you have to have certain intersections of this feed line with this tie line here. So at this limit, we can say that very small amount of extract at this at G. Okay, because we have to apply this lever rule, at least this line has to be inside this phase diagram. So that's the limit actually. Okay, because we can also write that E over R at any general point is nothing but RD, okay, over DG. So any other line, we can think of these ratios to these ratios. All right, one should also compare this, with this distillation column. If you recall from your previous knowledge that we had this TXY diagram, and we said that if we take certain binary mixtures of liquid and heat it, the first bubble is formed at this bubble point. At this locations, of course, we have very small amount of vapor form. So when you want to apply the tie lever rule, at least you have to be set inside. In that case, you can say that the amount of liquid over vapor is the ratios of this segment to this segment. Here it's a limiting case. In here, you can say that a small amount of vapor is formed. Similarly, if you start from here and condense it, then the first location you can say that we have a this is a tie rule, you can say the very small amount of liquid is formed. So that's a limiting case, minimum amount of liquid is formed. We want to apply a tie rule or lever rule, you have to be inside this phase diagram. So similarly here, in this case also, in this case we can say that very small amount of extract is formed. Of course, as you go along this, then we have large amount of extract formed. Okay, so the ratios is given by feed compositions and whatever you have, intersections of this line with the raffinate, this side of the phase diagram and the other side of this phase diagram. Okay. So similarly, let's look at other scenarios where we increase the amount of solvent. So in this case, we will address that this is very similar to what we had in case of absorptions, where we had this spent liquor concentration increasing or decreasing with the increasing or decreasing amount of the solvent. So let's look at the other scenarios where we increase the amount of the solvent, and let us monitor the locus of this mixing point. So we have ABC, this is the phase diagram, we have the feed, and we are adding this solvent here. So we have this YS, S you can call it, then we have this F, then we have this XF. Let's say we have this XM here, we have this tie line which goes through E, and then this goes through this R here. Now if you keep on adding more amount of solvent, then this location, this XM will move in this directions. So you have situation like this, then you have moves here, then you have another tie line which goes through this. So what is the limit? Again, you can expect that at this locations, when you have the tie line passes through this gives you another limit. All right. So here you can say that this is the maximum amount of solvent, you can add here. Okay. But more important here is to note that this composition, suppose we have let's put a name here, suppose we have this Y1 here or Y max here. All right. So this Y max is the concentration, is the lowest amount of C in raffinate phase. All right. So now what we are trying to say here, that as you go along this, then the amount of raffinate is very small here. All right. So when you go to this extend this, you have some coordinate here and you have some coordinate here. All right. So these compositions cannot go below the equilibrium concentrations of what you have in case of this YS. All right. So if you want to further lower this, it's quite obvious that we have to take a solvent which has a smaller amount of solute than this what we have YS here. All right. So in this case, we have seen that when we change the amount of the solvent, the coordinate moves in this directions and in this direction. So we have essentially two limits. So if this is a phase here and this line is fixed, one limit is given by here and another limit comes from here. All right. Here we have very small amount of extract and here we have very small amount of raffinate. So this is what we were trying to compare with the TYX diagram, that you have two limits where we have very small amount of liquid is formed, and when you go from this, very small amount of vapor is formed here and here. So these are the two corresponding points we were trying to discuss here. All right. This concentration is always greater than this YS. Okay. So similarly here we can write that S1 over F max, we can write at XF. Let's call this point as K. So XF minus XK over XK minus YS. So we are talking of this line here, this is XF, here this is XK, and this is your YS. Alright, so again apply the mixing rule to answer what is the maximum amount of solvent which will give this composition of xk. Alright, which is larger than this ys. So if you want to have larger this concentration of the solvent, or we want to further decrease this, we have to decrease this ys. You should be able to monitor, how does this xm moves and what are the two limits we get here and we get here. All right, and finally we must say that whatever we have done on the triangular diagram, this can also be done on this rectangular coordinate system. So if you recall that we said that we can also plot yx versus weight fraction of b. So we have xb and here we have yx or xy, then we have this phase diagram. So instead of triangular diagram, this coordinate system also works. And if you work on this type of this type of coordinate system, then also we have the same procedure of doing our calculations. We have marked this xf or yf. Let's say we mark xf and we have the solvent ys. So we can do the similar argument that this coordinate will give you minimum amount of solvent, and here we will get the maximum amount of solvent. In general, anywhere in between we can have m, xm. We apply the mixing rule between this and this. Then we find the tie line which goes through this, and we have this extract, and we have this raffinate. All right. So this is a discussion we had for this single stage. Let's try to understand and recall before we take up this multi-stage or double stages. All right. So in the single stage, we are bringing feed and we are bringing solvent, two in contact. Then we have mixing. We apply this mixing rule. Then we allow them to settle. So we have extract and we have this raffinate. Now we bring the second stage. Now the second stage, again we work on the raffinate and we connect this raffinate to this solvent. So we have similar story that first, again the second stage also consists of a unit which is a mixer, and then we have a settler. So every time you have 6 equations. All right. What are those 6 equations? We have one for your material balance for both mixer as well as for you have a settler. Then you write down the species balance for both mixer as well as for the settler. Then you have apply this tie rule. All right. Tie rule apply, which passes through this mixing curve, which gives you the 2 coordinate systems. All right. So these are mathematically these are the general equations which should be applying for every stage, multi-stage. All right. And the more important here is that we should be able to mark those coordinates on this triangular diagram or this rectangular diagram. So let us take now this multi-stage cross current extractions. So we have multi-stage cross current extraction. So now let's take one stage. We have second stage and we have this third stage. So we add feed F with the composition XF. We add solvent, say amount is S1 and this composition is YS1. So we have this extract E1 and let's say composition Y1. So we have this residue or the raffinate R1 and X1. So we have molar flow rate, some F kg per second, sorry, F moles per second. This comes to this stage. So one actually consists of 2 units. We talk it's a mixer, and then we are separating. And if it's an ideal stage, then these 2 streams are in equilibrium. Bring this to the second stage, where again you can add different amount of solvent with some different composition YS2, or we can say that YS2 is same as YS1. Then you have this E2 and then you have this Y2. Similarly, this treated residue or the raffinate is R2, X2 is brought to the third stage, where you add some amount of solvent S3 again with some composition YS3. You have this raffinate phase E3 with composition Y3, and then you have R3 with composition X3. One can also mix all these 3 and can collect some composite extract, and every time the second stage or the third stage, the leaving streams are in equilibrium, if we say that these are ideal stages. All right. So we have 3 stages. Essentially, there are 3 mixers and there are 3 settlers. Each mixer has 3 equations. All right. One mixing rule for the one equation for the mixing, another for this for the settler. Then you write down the species balance for the mixer and for the settler, and then also you have one for tie lines. This extra constant saying that y1 is in equilibrium with your with the extract and the raffinate phase. So each 3 mixers, we have 3 equations. Settlers also you have 3 equations. And let's now plot on this equilibrium curve on this triangular diagram. So we have A, we have B, we have C here. Let's say this is the phase diagram. Okay. Let's say this is the feed F, and we have this XF. So as usual, we connect with say some S. This could be pure solvent, or we can have some amount of solute C here as YS. Let's assume that YS1 equal to YS2 equal to YS3. So when we add this YS with certain amount of solvent S, then we say we have with this mix M1 here. We find the first tie line, we find the tie line which passes through this. We have extract E1 and we have this X1, which is like raffinate, and here we have this Y1. So that's a one mixer or one settler we had. Now what we are doing is that follow this schematic or the arrangement from one, we have brought to the second stage. Here again we add the second solvent. So from here now Rn1 X1 is here. Now we connect this, let's say, with the same amount of solvent. All right. So earlier we had the feed composition was XF. Now we have brought down this composition to X1. So this was XF. Now the weight fraction of the solute is X1. In this add the second solvent. Now we have this M2. Again find a tie line which goes through this. So we have E2 and we have this Y2. Similarly here we have this R2 and its composition is X2. Now it goes to third stage. So again from here connect this to this same coordinates. If you assume that the solvent YS, YS, and the third stage still you have the same YS3. So again you apply the mixing rule. Now maybe we have here you have M3. Find the tie line which goes through this. You have extract E3, composition is given as Y3, and here you have now R3 raffinate with the composition X3. So that's your product. All right. So essentially we have reduced the weight fraction of the solute from XF to X3. That's our raffinate. And for that we have added 3 times, or we have added the solute in 3 stages, and the extract composition changes from Y1, Y2, Y3. Of course one can collect all this, right, and you can have the composite withdrawal. So in general now we can talk of this equations here. Now if we have in general say n stages, it's not difficult to write down this balance. So overall balance for the nth stage. So if it suppose it's the nth stage, you are adding, you have a raffinate coming from the previous stage, so Rn minus 1. You are adding a solvent to this nth stage of Sn. This will be equal to Mn mixture, and then you will have this separation given by this tie line En plus Rn. So we are following the same nomenclatures, that suffix n signifies or denotes the stage from where that stream is originating. So raffinate was coming from previous stage, which is n minus 1. Solvent comes from the is fed to the nth stage. So we have Sn and En plus Rn here. Similarly, if you make a species balance, so we have Rn minus 1, Xn minus 1 plus Sn Yn, or you can call it Ys, which is constant in our case. So generally you have the one solvent which is fixed, which has a fixed quality for all the stages. So you have SnYs, or you can have SnYn as well to make it general. This will be equal to Mn. Then you have X, M, N, M for the mixing and N for the nth stage. This will also be equal to En, Yn plus Rn and Xn. Only thing you is note that Y1 and Xn, they are in equilibrium. They are given by this equilibrium curve or the tie line. So this is extra constant. You have one equation, you have second equation, third, you have fourth, and you have this the fifth stage, this tie line. Okay. So similarly, we can write down the set of these algebraic equations for all stages from 1 to n to do our calculations. Again, finally, we make a note that whatever we have done for this for this triangular diagram, we can also done for this rectangular coordinate system. So there also again you have this y and x compositions here. We have this xb, weight fraction of the solute. You will have phase diagram, and you can do the same thing there also. Take this f, connect with this s. So we have this xf, or we have this f here. Find m and do like this. Then you find, connect with this. All right. Then you have another mixing m here. Find another tie line going through this. Connect with this x. You have another tie line going through this, etc. We can do this all extract, and this all is raffinate. So one can also apply this. One can also make use of this rectangular coordinate system, where we have this xb weight fraction as this is the weight fraction of solvent. So either equilateral triangular diagram or triangular graph or this rectangular graph, both systems will work here. Now let's look at different system. Say we have insoluble liquids. All right. So far what we said earlier, that we have the system where two phases, this was A, this was B, this is partially immiscible. So that's why we got this type of phase diagram. So C is completely soluble in A, C is completely soluble in B. Now we are saying that, and A and B, they were partially miscible. But now we are saying that let's look at the system where A and B, they are completely insoluble. All right, completely insoluble here. So earlier, if we take a mixture here and we separate, they will separate in these two cases, this phase diagram. If we take here, they will also separate in these two weight fractions. But now if A and B are completely immiscible, then we don't have any phase diagram here. We don't have any equilibrium line intersecting this AB equations. All it means, we are looking at this type of system where we have A and B completely insoluble, and we have C which is getting transferred into this. So recall that this is a much simpler case here, and in this case we can have a much simpler phase diagram, just like represented in the earlier first few lectures when we talked about the different cascades. So in this case, y versus x will work very nicely. All right. So instead of working on this equilateral triangular this graph, now we can work on this coordinate system. So you must recall that, and you must realize that in this case, when we say that A and B, they are completely insoluble, so it's only C is getting transferred. This case is very much similar to a binary component discussion we had earlier when we did this cascade systems. So in other words, we can have C over B plus C. So this is the weight fraction of C in the extract phase, and we have this C over A plus C weight fraction of C in the raffinate phase. One can also write Y prime as a solid free basis, C over B, and we can have C over A for X prime. All right. So all we are trying to say that for such type of system, when A and B are completely insoluble liquids, this type of equilibrium diagram y versus x will be sufficient. So in this case also, if you start say certain phase, certain feet, so let's take that we have nth stage, and there you bring A, you add with solvent B, all right. So you have a raffinate and you have this extract here. So if you suppose you want to work on this solid free basis, so this Bn will remain as Bn. If you are adding it An minus 1, this will remain as An minus 1 here. So this is all solid free basis. An minus 1, An minus 1, this will remain the same. Let's say that this is A. Let's say this is same as B. Okay, we have the quality of this Ys solvent, solid free basis. So prime means solid free basis. We have this feed composition xn minus 1 prime here, okay, and so forth. We have this xn for the nth stage, and this is your yn nth stage, or yn prime or xn prime here. So we can write down this balance for a xn minus 1 plus bn ys. This will be same as bn yn prime. So notice that bn does not change because we are working on solid free basis. Okay, plus we have a xn prime. Alright, so it's just simple as species balance which you have made across that nth stage, and then we can write that a over bn. You will see why we are writing like this in a minute. A over bn will be equal to ys prime, maybe let's make a prime here for solid free basis, yn prime over xn prime, alright, xn prime here minus xn minus 1 prime. Okay, so essentially you can go back to this y versus x diagram, or y prime over x prime. Suppose this is a phase diagram, and this is say the solvent. So this the quality of the solvent is here is fixed as ys prime. Now the first stage, let's say that we start with certain xf prime. So this xf prime is brought in this contact with this ys solvent. So we have this coordinate. From this it's very easy to make out that now you have a operating line with the slope of minus a over bn. So take the slope. Now this line reaches here. Alright, the stage, first stage, we are adding the solvent, and we have the raffinate and extract phase. They are in equilibrium. A and B are completely insoluble, so we can write this type of diagram will be sufficient for discussions. So the two streams are in equilibrium. We take all this way till it intersects here. That's the first stage. This stage is again brought in contact with the same quality of solvent. Again you take difference in that slope of minus a by bn. If the amount of solvent is same in all the stages, then these slopes will be, these lines will be parallel. Alright, so I can come back to this. We're here, come back to this. So essentially you go down from xf to all the way to this whatever concentrations you have. You must not notice that you cannot go below. Alright, so this is all your equilibrium line. So when this operating line, it intersects with this equilibrium compositions. So that means suppose the last stage, this ys is in equilibrium with this x here. So all it means we can write down the no raffinate. So this is the raffinate here. Alright, so this is raffinate, it's all raffinate, 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 and here we have this extract, extract, extract. So no raffinate of concentration smaller than that what you will get in this extract phase, solvent phase is possible. That means suppose in some stage you reach here. So what is the composition of this raffinate? It's in equilibrium with this extract phase. So you cannot go below this, which is in equilibrium with this. So that's the limit of your treatment. That means starting from xf prime, you cannot go below this. The last stage, the composition of whatever is extract phase in equilibrium with this raffinate. So if this is the last stage Nn, this is Yn, this is Xn, Xn is in equilibrium with Yn. So Xf cannot be, or this treatment of the last raffinate cannot go below this Xn. So that's the limit here. To go below this, again you must realize that you have to go below this. You have to lower this quality of your solvent here. In that case, it's possible that we can go below this, whatever was the desired in our earlier case. All right. We did single stage, then we did multi-stage, cross current, and now we do the last one here, multi-stage counter current. Okay, so essentially what we have now, we have multi stages, however the mixing is cross current. So let's say we have stage 1, 2, and then we have a general stage here S, and then we have last stage NP, number of plates or stage is NP. So now the feed enters at the flow rate F with the composition XF. Okay, so this feed is again kg per second, XF is kg per kg, all weight fraction, and then we have the solvent, fresh solvent, which enters a counter current. So that's what we are doing, multi-stage counter current. So we have S, which is like B, pure solvent, and this may have some mole fraction, let's say Ys, may not be 0. Okay, so now we have the feed, so the numbering would be now R1, raffinate residue, mole fraction, weight fraction X1. So we have now R2 and X2, and let's take a break here. All right, so let's put a break here, and then we have this raffinate RS and XS. So that's the specs for the stream which enters the stage S, and then again let's take a break, and the last stage we have R NP minus 1, and this treated in the effluent is now R NP, and the weight fraction is X NP. Okay, so similarly we have the same nomenclatures here. This would be extract, so ENP, because it originates from the stage number N, and we have YNP. Okay, so for this stage S, this is ES plus 1, because it's counter current, it originates from the next stage, and we have YS plus 1. Similarly, this would be ES, this is ES, sorry. So here we have, this should be ES, and we have YS, and then we have, this should be, it originates from E3, so E3, Y3, we have E2, Y2, then we have E1 and Y1. So this feed enters from here, and it's in counter current with the solvent S or B with the weight fraction Ws, Ys, and we have this treated effluents. So the composition of this raffinate or the feed after the nth stage is XNP. We have brought down the concentration from XF to XNP, and the solvent concentration will increase from a very small quantity Ys to Y1 as this component is transferred every stage. So look at the nomenclatures, we are still following the same convention. The number and the weight fractions has a subscript which denotes the stage from where it has originated. So that's a multi-stage counter current. Unlike in the previous case, multi-stage cross current, we had to add the feed separately. Okay, so this is a raffinate, and downstream we have extract stream. So up we write raffinate, here we have this extract. So now let's make this overall balance here, F plus S. So 2 overall feed enters here and S enters here. Alright, then you have M, so it's mixing, so you can always write F plus S as M, which is overall it's E1 plus RNP. So this is the overall balance. F plus S equals E1 plus RNP, 2 entering and 2 leaving, same as M. Similarly, we can write FXF, species balance SYS equals MXM equals E1 Y1 plus RNP XNP. So overall material balance and the species balance. The physical meaning of XM is both ways based on the feed, 2 entering stream FXF plus SXS equals F plus S, and this will also be equal to 2 leaving streams E1 Y1 plus RNP XNP over E1 plus RNP. Of course, you must understand that this M or XM doesn't have any physical entity on this in the system here. The 2 streams F and S which enter, they don't see each other. Similarly, the 2 leaving streams E1 and R and P, they leave from the 2 ends. So this M is only hypothetical points, mathematical points, signifying summation of 2 streams F plus S, E1 and R and P, or you have the weight corresponding weight fractions. All right. So here also you must not we follow the same nomenclatures, that all operating lines connects say Y2 versus X1 or Yn plus 1 versus Xn. So let's go back to the previous schematics which we have. R1, you have Y2 and X1. That's the material balance will give you operating lines. E3 and X2 operating lines. And if it's ideal stages, then X1, Y1 will be in equilibrium, X2, Y2 will be in equilibriums, and so forth. All right. So Y2 versus X1, Yn plus 1 versus X1, they come from the operating line, and the equilibrium line or the tie line, if you have ideal stages, then you have Yn versus Xn, or Y1 is in equilibrium with X1, Y2 is in equilibrium with X2. So we are following the similar conventions which we followed in the previous unit operations when we had a displacement stage wise. Okay. More here important is that note the difference R and P minus S. So we are writing it from the previous balance which we made. We wrote F plus S equals E1 plus R and P, which means R and P minus S equals F minus E1. And this will also be equal to at any general stage Rs minus 1 minus Es, or you can have Rs minus Es plus 1. So the difference is constant, and this should remind us that we have a difference point here del R, which is very similar to what we did in case of distillation column when we marked the difference between the 2 streams. So go back to the previous schematics which we can redraw here. If there are the stages, stage 1, stage 2, feed goes in this directions, and we have the extract going in this directions. So this is a stage, and we have 2 streams getting in like here. The last stage we have NP. So the difference between any 2 streams here, molar flow rates of the 2 streams anywhere, it's a constant given by del R here. So we have R and P. So this is R and P, and this is S. R and P minus S is same as F minus E1, or it's same as for stage S. This is RS. This is ES plus 1. So the difference between the 2 is del R. Or ahead of this, you have RS minus 1 definite, and you have this Es plus 1. So this difference is also constant, and that's what we are denoting it by del R. So this is very equivalent to previous balance which we did for distillation column to identify this difference point. All right. Now let's mark these points on our equilibrium curve. Let's start with rectangular coordinate system. That means we are working on this A, B, C. We are plotting weight fraction of B on x-axis, and on the y-axis we have weight fraction of raffinate and extract, x and y, and we have this equilibrium curve which is like this. All right, so instead of equilateral graph we can also work on this rectangular. Okay, so start again with the feed. So let's say this is F, and feed does not contain any B, so we have this coordinate marked here at xf on this AC line, and let's say the solvent composition is Ys. All right, so this Ys is same as, it represents ENP plus 1, extract entering the last stage. So again you should go back to the previous schematics for different stages. All right, so we have general stage here S, and we had interruptions here like this, like this, like this. So this is stage S, the last stage. Feed comes like this, and solvent goes like this, counter current. So stage 1, stage 2, we have this feed F, and we have this extract originating from 1. So this is E1, and this is ENP plus 1, which is same as S. We said molar flow rates. This has a composition, let's say Ys, very small amount of solute C here. It's possible that solvent is pure. In that case, Ys may lie on this line AB. Let's take ES here. All right. So this is raffinate. So this would be RNP, and this is XNP. And here we have F, XF, and this is Y1. So this is Ys, this is Ys plus 1, this would be XS minus 1, and XS. So same nomenclatures. So let's start with F here and S here. Okay, so we know F, quality of this feed, and the quality of this extract or the solvent which is being used here. If we know this, we can connect this. We can find out M, mixing. So this is your M here. Now again we said that this feed is here and solvent is here. They don't see each other. This M is only a hypothetical point. It's a mathematical point which represents the composition of the mixing of F feed with the solvent, which is M here. All right, and we also know that E1, and we know this R and P. So these 2 points can also be marked. All right, so essentially we have treated this solvent from X and P. We have got down this level to this X and P. So let's say X and P is somewhere here, X and P. So X and P is in equilibrium with this Y and P. All right, so let's mark this point here. Okay, and similarly if we know E1 extract here, we can mark this point here. But more important to note is here that this line, operating line, has to pass through this. So this is E1 and this is Y1. All right, so again please note here that F and S, 2 entering streams, and we have E1 and R and P, 2 leaving streams. They don't see each other, right, in the previous like cross current. But so that means this M, what we're writing down here, is only a mathematical point, does not exist anywhere on this system. So F, Ys, M, they will lie on one straight line, and this M point will also lie on the straight line connecting X and P and Y1. X and P here and Y1 from the mixing rule. So we have marked the 4 exit streams here, 1, 2, 3, and 4. Now we can start drawing the construction for the stages. So we realize here that E1, Y1 is in equilibrium with X1, ideal stages. Now with this E1, we can draw a tie line which, let's say, goes through this to give us x1. So we have marked x1 here. All right. How do we proceed? This is x1 and now we have y2. So now we are talking of this operating points. How do we reach this y2? Okay. Just now we said that difference between any of these two streams, F and E, RNP and S, ENP plus 1, or x1, y2, xs minus 1, ys, or xs, ys plus 1 is a constant. That means if we draw these two lines and extend, and these two lines f1, this f which you have drawn here, and e1, they will meet at point which we call it del m. So you can try to understand, we are trying to locate this point here. All we are trying to say that difference between f and e1 or any two streams xs minus 1 ys is a constant on the material balance. So once we locate f e1, we can extend, and once we locate ys and x and p, we can extend to operate this del m points. Once we have the difference points, now we can start constructing outer stages. We have y1, so now we have x1. How do we get y2? Again we connect from here, this x1, again one has to connect to this operating line del point here. Alright, so if you connect this and extend, you will get E2 corresponding to this y2. Take this, draw the equilibrium curve to obtain x2, connect with the del point and extend, you have E3 and y3. And then similarly you take stage equilibrium here, take this equilibrium here, you get your x3, etc. So you have stage 1, stage 2, stage 3, and so forth till you reach the stage. So here we are trying to understand our methodology. We have the same story, yn plus 1 and xn, they are connected with the operating line, and yn and xn, they are connected with tie line or equilibrium curve. And how do we obtain this? We look for this del m difference points. Difference points, how do we get? We realize that difference between the weight fraction, weight flow rates of any two streams are in this conjunct is a constant. So knowing f and e1, extend here, and knowing ys and r1 here, the difference between the two is a constant, extend, you get this del point. Once you locate del m point, just like in this distant column, start with e1, you get x1 by tie line, connect x1 with I2 through this del points, extend, you have y2. Find the other tie line, this gives you x3, x1, x2, x3, etc. Keep on constructing this line here. Just to conclude here, you can also have this different situations where the del point can lie on the other side of the graph, which means suppose you have equilibrium curve like this, all right. Suppose feed is here, and if we add, now this is a solvent, and extend this, we have mix. Now if you add more amount of solvent, you should be able to make out that this location of m will move this direction, because you are taking a more and more solvent, larger amount of solvent here. So this point will move in this directions. And then if you knowing this, suppose this is your x and p, if you extend this, this will give us E1. So as m increases, you can see that E1 will decrease. This location of this point will move like this. Earlier we had E1 here, now it moved to this, it moved to this, as you increase the amount of this solvent. So it's possible that when you extend F and E1 and extend R and P and Y and 1, they may extend and connect somewhere here as a del M points. So in this case, all we are trying to say that E1 is less than F. The previous case, we have less amount of solvent, E1 was greater than F, right? This location of E1 was higher on this F. Here it is, weight fraction of this E1 is smaller than weight fraction of feed. So we have locations here, so that the 2 points when you extend, they increase del D. So whether this side or this side, del M, our principal methodology is the same. The difference between the two streams, y np plus 1, right, and xn is given by this del points, and xn and yn, they are related by this tie line. So anywhere if you extract, you draw a tie line, is given by y1 x1 or y2 x2, y3 x3, etc. And when you connect with the operating line, that gives you yn p plus 1 xn1. All right, so it's whether the del m point is this way or this way, it all depends upon the amount of solvent, locations of m. It doesn't depend upon what type of equilibrium curve we have. It all depends upon the amount of solvent which is added. So m moves this way, extract location moves this way, or upward if you decrease the amount of this solvent. So today's lecture we conclude here, and the next lecture when we start, we will address the minimum amount of solvent required or what is the maximum amount of solvent, very similar to we have the treatments for the cross current, or in fact in the distillation column or the absorption columns. Okay, and then we will take some example on this 3 stages. We have 3 types of arrangement we have. One was single stage, the most simple. Then we had the cross current stages where we added the solvent, fresh solvent at every stage, and then we have this counter current stage. So we will take these examples in the subsequent classes on extractions. Very good. ठीक है.